Hello, we're going to take a look at decision trees and we're going to see how to read decision trees, and also we'll get some understanding on how decision trees are created. We'll also get to see some decision tree that is output by SAS. Well, decision trees are useful for classifying observations, and if we have a data set of customers of a bank or who have taken some loan, and you have data on customers who have defaulted on the loan versus customers who did not default on the loan. So if you have data on nominal values, somebody defaulted or not defaulted, and you want to be able to classify customers and also try to find out which customers will likely default and which one will not default. To make those kind of decisions, decision trees are useful. You create a decision tree by using existing data, and once you have a decision tree created using existing data, then you can use the decision tree to predict probability of outcome for new data. So if you have and these probabilities can be figured out by a series of if then else type rules. So the idea is we want to be able to classify observations, and the observations based on nominal data or binary, which is two values, or it could be ordinal targets, maybe multiple values, and not a whole lot of unique values maybe, and also we can also use it for predicting outcomes of interval type targets, not only nominal type target but also interval type target. Decision trees are very easy to interpret, and they are, once it's created, and people can just go down the decision tree to make a decision. And take the case of a simple financial institution that wants to know whether a customer will default on a loan or not, and to come up with a measurement of whether somebody will default or not, they use a bunch of inputs. So they have, for each of the borrower, they have data on how much debt to income ratio he has, what is the property value, and how many times has he been delinquent on payment, and what is the first mortgage, how much was it, and how long ago was the oldest loan. So we have data on all this, and they want to try and see if these inputs can help them classify customers as somebody who might default or not. Now this is a decision tree. Decision tree, this tree is upside down tree, and what we have here are we have the root node, which is one of the input variables is chosen as a root node, and from the root node we split the entire data set based on whether the root node value is certain bit below a certain level or above a certain level. So in this case we split the entire data set on whether the debt to income ratio is less than 45 or more than 45. And once we have split it, and among the ones that are less than 45, they find 7% of them have defaulted, and 64% of them have, and 93% of them did not default. And with debt to income ratio more than 45, 64% defaulted and 36% did not default. So debt to income ratio is a very good initial input variable to broadly classify customers as defaulters or not defaulters. Now we go on to applying technique for building this decision tree. Once we have this split up based on debt to income ratio, and then we will split that small set into further subset the next time, maybe using a different input variable. Say for example, after having separated the debt to income ratio of those with less than 45, we look at the property value column, and we find those with property value less than 300,000 have a 6% of them defaulted, and 94% of them did not default. On the other hand, those with property value more than 300,000, 79% of them defaulted, and only 21% did not default. So after having split the entire sample based on debt to income ratio, we split that first part further on property value, less than 300,000, more than 300,000. And after that, we can, for those whose property value is less than 300,000 and whose debt to income ratio is less than 45, then we look at delinquencies. Okay, and then those with less than 6 delinquencies or more than 6 delinquencies. If somebody has less than 6 delinquencies, then only 6% of them defaulted. Somebody with more than 6% of delinquencies, or 100% of them defaulted. So in other words, we split the data further at each of this point, and the nodes, what you see inside nodes are called regular nodes, and the starting node is called the root node, and the ending nodes are called leaf nodes. And on each ending node or each leaf node, we have the expected value calculated. Say for example, if we reach this node, there is an 83% chance of defaulting. Okay. Now once a decision tree has been built up like this, it can be used for predicting outcomes for new cases. So let's take a look at a new case. Okay, new case has a debt to income ratio of 20 and property value of 500,000. Delinquencies is 0 and first mortgage is 200,000. So debt to income ratio is 20, so we go to the left side from debt to income, and property value is 500,000, which is more than 300,000, so we go to the right on property value, and delinquency is less than 0. Delinquency is 0, so that doesn't really count. First mortgage is 200,000, which is less than 246,000, so there is a 92% chance of delinquency. Okay, so that is that's how we can use this decision tree to predict outcomes of new cases. All right, now at each node that we looked at, a 2x2 contingency table is created, and then the Pearson coefficient is computed, and the Pearson chi-squared statistic is calculated, and p-value is calculated, and based on this p-value, some contingency tables, some splits are included in the tree and some splits are not included in the tree. The logic of how p-value is used in deciding on whether a split will be included or not is explained in the book. There is also some notes available on SAS website, So I have a link to that here, but not link, but the URL, and this link is also available on class modules. And here we have the output as generated by SAS Enterprise Miner is a little different, and it starts by it doesn't really have the leaf kind of a structure, but mostly boxes. And so start now. Here's a decision tree that is the result of a mail-in customer survey conducted by HomeStuff, a national goods retailer. In the survey, customers had the option to enter a cash drawing. Those who entered the drawing were classified as HomeStuff best customer. Best customers are coded with 1 in the decision tree. Now if you look at this diagram here, so they got data on whether the customer is male or female. So F female, M for male. So gender data is there. They also have data on total lifetime visits, and if it is less than 3.5 to 4.5, or more than 4.5. So these are the 3 categories where the total lifetime visits have been split up. And they also have data on net sales, whether net sales is less than 281.5 or more than 281.5. So this decision tree has been built, and the lines linking the nodes give you the cutoff basically for selecting the left or the right. And inside the box we have percentages. So 1, the target variable is it's a classification of either best customer or not. So 1 means best and 0 means not best. So overall in the data set they have, before even split up on gender, overall in the data set, the very top root node tells you that 57% of the customers are classified as best. Now if you go down to gender female, 59% are classified as best. Or if you look at the gender male, 54% of males are classified as best. And so every box, subsequent box, has what percentage of customers are classified best and what percentage are classified as not best, and also have a number of observations. So once you got this kind of a diagram, then it'll be easy to read and answer questions. So the question we would like to answer is, what is the probability that a male whose total lifetime visit is 4 and has a net sales of 280? Now, so male is what we want. So we want to go to the right side of the branch here, and total lifetime visit 4. Now once you come to male, lifetime visit doesn't really matter, whether it's 4 or more does not matter. Net sales is 280. So net sales, if net sales is less than 281, then we come to this box, with 1 or best customer percentage is 45 and not best customers percentage is 55. So the answer to this question will be 45%. The probability is 0.45 that the new customer will be classified as a best customer. So I hope that was clear enough to understand what decision tree is, and decision trees can be created using SAS, and we'll see how to do that in just a minute. Thank you.